In PIC18 microcontroller, we have ADC module inside the architecture. Now, this ADC will be beneficial for whenever you are taking sensors that are connected with your microcontroller. At that time, we can use this ADC module. Usually, sensors are of the two categories of nature. One can be of analog or other one can be of digital. So it may happen that whatever the quantity which you will measure it from the analog or from the digital, most of the sensor will work with the analog category. And as your microcontroller processes all kind of signals in the form of digital signals. So we require some kind of converter to convert this analog quantity into digital one. So for the purpose of conversion, we require this ADC, which will simply convert this analog quantity which is coming from the sensor, and it will get converted to the digital form, and then this digital data you can pass on to your microcontroller for the further controlling. That's why we require the ADC in any embedded application. Now in PIC18 architecture, we have individual ADC module within the architecture itself. Now this architecture ADC will be 10-bit analog to digital converter module will be there. Now this 10-bit ADC has 13 channels. So those are named with the reference of AN0 to AN12. These 13 channel, you can say that you can connect at a time 13 sensors to the PIC architecture. Through that you can control the 13 different sensor to the microcontroller. So just because of we have 13 channels, that's why this 13 different sensors we can connect to the ADC module. Now here the 10-bit meaning is nothing but 10-bit conversion. So nearly it will take you around to the 2 to the power 10 bit. So in a range of 0 to 1023 range will be there for the converted digital data. Whenever you wanted to calculate the resolution for ADC, the basic formula will be ADC resolution equals to your V reference divided by 2 to the power n minus 1. And here n is nothing but your number of bits for the conversion. In this particular ADC, we have this n is equals to 10 bit. So like that way, you can calculate resolution for the ADC. Now this is pin out for PIC18. But if you carefully observe this pin diagram, in PIC18 architecture, as every pin is multi-pin function, so all the 13 channel which are highlighted in red, those are nothing but ADC channels. This is ADC block diagram. So as per this block diagram, you can able to see all the 13 channels right from AN0 to AN13 are 12 are connected to the one of the selector. So selection of channel is through the CHS3 to CHS0 bits. So these 4 bits are part of the one of the control register. Through the software selection, you can connect any of the channel out of this 13. So if you have connected temperature sensor at AN0, so in that manner, for the selection of this channel, you will assign these 4 bits as a 0000 in control register. So as this ADC is SAR, successive approximation ADC, so there is a reference threshold voltage. So whenever sensor data is coming from one of the channel, that will be considered as your V in, that will get compared with your V reference voltage. This V reference, there are two options. Either you can select V reference plus and minus or VDD VSS. If at all VDD VSS there, then the reference voltage will be 5 volt. Otherwise, for the V reference plus and minus, it is 3.3 volt. So if V in is greater than V reference, then it will be considered as logic 1. If Vin is less than that of reference threshold, it will be considered as a logic 0. So like this way, digital conversion will be taken place under this ADC. In order to program this ADC, we require basic configuring registers. Those are 5 register: ADC result high register, ADC result low register, ADC control 0 register, ADC control 1 register, ADC. So as this ADC is SAR, successive approximation ADC, so there is a reference threshold voltage. So whenever sensor data is coming from one of the channel, that will be considered as your V in, that will get compared with your V reference voltage. This V reference, there are two options. Either you can select V reference plus and minus, or VDD VSS. If at all VDD VSS there, then the reference voltage will be 5 volt. Otherwise, for the V reference plus and minus, it is 3.3 volt. So if V in is greater than V reference, then it will be considered as logic 1. If Vin is less than that of reference threshold, it will be considered as a logic 0. So like this way, digital conversion will be taken place under this ADC. In order to program this ADC, we require basic configuring registers. Those are 5 register. So here is very first controller is register, ADCON0 register. This register is used for the channel selection. All 13 channels will be selected by these 4 bits. Next control register is ADCON1 register. Now this ADCON1 register will help you to select your reference threshold voltage. So that is nothing but this particular reference configuration bits will be specified in the diagram. That bits are resident of ADCON1 register. So these are the content for your ADCON1 register. So from this 5th bit and 4th bit, you will able to have the reference of voltage reference configuration either of plus 5 and minus 5 volt, or for the case of V reference and plus and minus 3.3 volt V reference plus and minus. So these configuration bits will help you to configure the comparative voltage reference threshold, whether it is 5 volt or whether it is 3.3 volt. That selection will be taken care by this 5th and 4th bit. By assigning these two bits as a 1 1 means you're taking the reference as a V reference plus and minus, and which is nothing but 3.3 volt. If at all you have selected VDD and VSS by assigning these two bits as a 0 0, then you can say that these two bits will be considered as a plus 5 and minus 5 threshold voltage for the conversion. Now in this architecture, every channel, as I have told you, that sensor are of two categories. One can connect analog sensor, one can connect digital sensor. So these 13 channel can play with the case of either they can act as an analog channel or they can act as a digital channel. So based upon your sensor category, whether it is relying into the analog or whether it is going it for the digital category. So likewise, you need to select the channel selection. So if at all you have connected 13 sensors and all 13 are analog, then you have to assign this configuration ADC port configuration control bits as a 0 0 0. So otherwise, if at all you wanted to connect all the 13 sensor in and all those sensors are digital, so in that manner you can assign the value as a 1111. So A stands for analog input, D stands for digital IO input. So for that purpose, you are converting this into the digital form. Third controlling register is ADCON2 register. Now this ADCON2 register will help you to get the result, and that is you will able to get it through your ADFM bit. Now this ADFM bit is nothing but the combination of your lower byte digital result ADC conversion result or higher byte ADC conversion result. So whenever you have wanted to store the result in the case of the digital number, in that manner, there are two ways to store the result. Whether you wanted to save it in the case of right justified, or whether you wanted to save in the case of left justified. So whenever you are saying that you wanted to store the result as a right justified, so for that ADFM bit should be 1. Keep this in mind. Now, as ADFM bit is 1, which is nothing but right justified, meaning is your ADC conversion data will get stored from lower 8 bits. Means it will start loading it from your low AD result register lower byte, and then it will keep on transferring the data to the higher byte. As this is 10-bit ADC, so you need to have the result as a 10-bit only. So lower 8 bits are occupied by your lower byte register, remaining bits will whichever channel you wanted to use. Like that way you have to give this binary number inside this bits. Go and done bit. Usually this bit is specified for the start and stop of the conversion. Register is ADCON1 register. Now this ADCON1 register will help you to select your reference threshold voltage. So that is nothing but this particular reference configuration bits will be specified in the diagram. That bits are resident of ADCON1 register. So these are the content for your ADCON1 register. So from this fifth bit and fourth bit, you will able to have the reference of voltage reference configuration either of plus 5 and minus 5 volt, or for the case of V reference and plus and minus 3.3 volt V reference plus and minus. So these configuration bits will help you to configure the comparative voltage reference threshold, whether it is 5 volt or whether it is 3.3 volt. That selection will be taken care by this fifth and fourth bit. By assigning these two bits as a 1 1 means you are taking the reference as a V reference plus and minus, and which is nothing but 3.3 volt. If at all you have selected VDD and VSS by assigning these two bits as a 0 0, then you can say that these two bits will be considered as a plus 5 and minus 5 threshold voltage for the conversion. Now in this architecture, every channel, as I have told you, that sensor are of two categories. One can connect analog sensor, one can connect digital sensor. So these 13 channel can play with the case of either they can act as an analog channel or they can act as a digital channel. So based upon your sensor category, whether it is relying into the analog or whether it is going it for the digital category. So likewise, you need to select the channel selection. So if at all you have connected 13 sensors and all 13 are analog, then you have to assign this configuration ADC port configuration control bits as a 0 0 0. So otherwise, if at all you wanted to connect all the 13 sensor in and all those sensors are digital, so in that manner you can assign the value as a 1111. So A stands for analog input, D stands for digital IO input. So for that purpose, you are converting this into the digital form. Third controlling register is ADCON2 register. Now this ADCON2 register will help you to get the result, and that is you will able to get it through your ADFM bit. Now this ADFM bit is nothing but the combination of your lower byte digital result, ADC conversion result, or higher byte ADC conversion result. So whenever you have wanted to store the result in the case of the digital number, in that manner, there are two ways to store the result. Whether you wanted to save it in the case of right justified, or whether you wanted to save in the case of left justified. So whenever you are saying that you wanted to store the result as a right justified, so for that ADFM bit should be 1. Keep this in mind. Now as ADFM bit is 1, which is nothing but right justified, meaning is your ADC conversion data will get stored from lower 8 bits. Means it will start loading it from your low AD result register lower byte, and then it will keep on transferring the data to the higher byte. As this is 10-bit ADC, so you need to have the result as a 10-bit only. So lower 8 bits are occupied by your lower byte register, remaining bits will. So ADC result will be stored in two register, ADRESH register, ADRESL register. But the result will be stored in either of the two form, with maybe in the right justified and left justified manner. So left justified will start loading the data from the higher byte register, result register, to the lower byte register, and whichever bits are remaining, that bits will get loaded or appended with zeros, like bit number maybe from 0 to bit number maybe from 5. So if at all, the result should not get exceed beyond the 10 bit, because the ADC itself is a 10 bit ADC. That's why result will be of size only 10 bits. So in that manner, this is the left justified condition where you are mentioning ADFM bit as a 0. So that is nothing but this. And whenever this ADFM bit as a 1, it will be considered as a right justified, where the result will be stored from D0 to maybe D8, D9, D10. So these two bits are from your higher bytes, and the bits which are remaining unused from higher byte register, that will be padded with the zeros. So this is nothing but your ADC result will be stored with the help of ADFM bit. In this register again, ADC acquisition time bits are there. So these 3 bits are ADC acquisition time. So the ADC acquisition time is nothing but considered as a sampling time. This particular acquisition time is also referred as the time required for the ADC converter to capture its input voltage during its sampling. So as we know that ADC here in this architecture is successive approximation ADC, SAR type of ADC. So the ADC will take out the amount of time required to charge and hold on the front end of the ADC, that will be decided upon these 3 bits. So these can be considered in terms of minimum 000 acquisition time will be there, and maximum 20 AD acquisition time will be given for this particular ADC acquisition time select bits. Last 3 bits are nothing but your clock select bits. So these clock select bits will be the, if at all you have connected the 20 megahertz crystal and you have enabled the clock frequency as a divided by 16, let's say by assigning 1012 these lower 3 bits. Means 20 megahertz will get divided by 16, that will give you around in terms of, if at all I wanted to calculate in terms of time period based upon this frequency and this particular conversion time, so it will comes out near around 1.25 microsecond, if at all I'll be able to convert this in the case of, if at all I'll be able to have the 20 megahertz. So 20 megahertz divided by conversion time is nearly 16. FOSC divided by 16. So here FOSC is 20 divided by 16, nearly 1.25 megahertz frequency will be there. So in that manner, you can able to have upon the look for the conversation for the time period. In that manner, 1 upon 1.25, nearly zero point 0.8 microseconds will be considered as your conversion time for your ADC. So like this way, you can calculate ADC conversion type based upon the clock that is been arriving for or applying for your ADC. So these are the 5 important registers that are required to program your ADC, built-in ADC for your PIC18 architecture. Now let's take one example as if at all you are connecting ADC to your PIC18s. Here instead of sensor I have connected 1K of port and that is connected to the AN0. So for this particular AN0 channel, I have selected one port and I need to convert that particular analog value which are coming in from the port, and that will be converted result for ADC will be displayed it on the LCD. So for this interfacing diagram, you need to write code, embedded C based code. So let's check it out in what manner we will be able to start writing the code for ADC interfacing with the, instead of sensor I have connected port. If at all you wanted to connect the sensor, you can connect that sensor by replacing this port. So to write code for ADC, flowchart will be start. After that, you have to initialize the port as an input direction wherever you have connected the channel for that respected port. After that, you have to initialize the channel. So as out of 13 channels are there, which channel you wanted to select, that respected channel you have to enable, and then you need to start your conversion. Once you start that conversion, it is mandatory to monitor that conversion by using the means of checking the status of whether the conversion is over or not. So in that respect, you can able to see that if at all conversion is over, the condition will be maybe the true condition and false condition. Is your conversion is not over yet, then you need to monitor at what state conversion will be completed. And if at all conversion is done, means you need to get the result from that channel. And as you wanted to display that result on LCD, as you know that basic concept that whenever you wanted to display something on LCD, it is mandatory to convert that data into ASCII format. So whatever result you are able to get it from here, that you need to convert into ASCII before displaying onto the LCD and end your code. So this is flowchart for ADC. With respect to that, you need to start writing code for ADC interfacing. So as basic requirement is there, here I have connected one, let's say LDR in this picture. So if at all light intensity fall, the LDR resistance will get changed. So in that manner, you need to check it out, convert that respected analog quantity which is coming from this LDR, that will be given to the ADC, and at the output of this ADC, you will able to have the binary numbers. So this binary numbers may get changed depending upon the light intensity that fall onto this LDR, and through which your data will be getting changed. So let's start writing embedded C based code for ADC interfacing. Very first line you need to mention is header file. So hash include P18F4550.h. After that, we need to mention system pragma settings using the pragma directive. So pragma config. Now as this pragma config is nothing but directive. So you are mentioning some of the setting. Oscillator selection is HS. Hash pragma config LVP off. Another watchdog timer setting, again it is off. And the last setting is port D, analog to digital, enable is off. So after mentioning the pragma settings, you need to define some of the port declaration. Now, as per the interfacing diagram, you need to connect LCD. Along with that, you need to connect the port to that respected channel. So for that purpose, I am defining some of the pins for the variable in terms of hash define, let's say LCD data. And I have connected it to port D. So all port D will be known it further as a LCD data. Another variable I would need to define is my control signal for ADC. So enable, and that is connected to port E. Bits, individual bit I wanted to access. So for that matter, I will write RE2. Next is your RW, read write signal. And the last is RS. That is 0. After that, some of the functions declarations are required here, but I'll just write those function declaration at the end. So here, let's say you wanted to initialize LCD. So very first function will be in the case of LCD initialization. So inside that you have to give, as you know that to initialize LCD, you require some of the commands. So very first command is 0x38. Delay. After that 01. This is clear screen. Delay. After that 06. Increment cursor left. Delay. 0C. 0C is nothing but display on cursor off. Then after that, we take first row, ATH, delay, and function will get complete. So this is nothing but your LCD initialization. After that, you need to start writing your LCD data. So here I will write void LCD data. And the parameters you will pass is unsigned char type of, so char CMD. So whatever CMD parameters will be there, that will be given to the data lines. Now as this is command mode of operation for LCD. So that's why RS is 0, RW is 0, enable will be 1. Now another function we need to write is void LCD string, where we have taken pointer for all the string elements will get displayed on the LCD data lines. So for that matter, we have taken this I variable. So this will be considered as your pointer till the string pointer becomes null. It will transfer the data on the LCD data lines. After that, we need to initiate ADC initialization. ADC initialization is nothing but setting your channel selection and turning on the module. So right now we are not thinking about to start your conversion. So initially just keeping the setting for the channel selection and module on. So in that respect, ADCon register 0B0000000001. So in that manner, module will be on, and as per this particular condition for channel selection, we have connected to the port to the AN0. So in that manner, we will be able to selecting the channel. Then the control setting for ADCon1 register. So this ADCon1 register is nothing but the condition for setting for the all the channels. So as per this particular condition for ADCon register, these channels will be considered in the way of as you are taking the consideration for AN0. So this is analog port which you have connected. So this particular channel is only turn out as analog, rest of the channel as a turn out as a digital, due to which you can able to have the possible value for this particular these four particular bits as a 1110. So you need to load that value in this ADCon1 register. After that, there is a consideration for the ADCon2 register. Now, this ADCon2 register is setting the result as well as for the justification for the acquisition time. And in order to that, you can have the conversion clock where you have considered this as a ADCon register with the conversion clock will be considered as, for the basic reference, it is been considered as FOSC divided by 64, and your acquisition time is considered as 280. So through which you can able to have the value as 0B10001110. So either you can give binary values to this particular registers, or you can give the hex values. So whichever is comfortable, you can assign these kind of bits in terms of binary or hex. And after that, you need to turn on the module. Now for start of conversion, you need to write one more function as start conversion. So start conversion is nothing but go bit has to be 0, and go bit is part of ADCon 0 register. That's why you will write ADCon 0 bits dot go equals to 1. So like this way you can assign the start conversion value for this ADC converter. After that, as the conversion will get taken place, at the end of the conversion, we need to get the result. So for that purpose, again, one more function is written, that is unsigned int get result. So inside this, I have declared one variable, ADC result variable. So this variable will be able to load the data once conversion is done. So for how long you're going to check the status? Till this go bit will be 0. Once it is done, you can take your result from your ADRESL register and transfer to your variable ADC result. Now, as 10-bit result is there and this register holds 8-bit of data, and remaining 2-bit of data is present in the H register, higher byte of this result register. So in order to that, while loading this data, pointer will reach out to one location. After that, we need to load the upper 2 bits of these two registers. That's why we will shift this respected pointer position to the 8th location so as to load the 2 bits from your higher byte register, and it will return the result. Just like the delay function which is mentioned, if at all you wanted to, if you don't wanted to use this random delay function, then I would suggest to use a timer. So with the help of timer, you can generate exact amount of delay using the timer calculation and timer programming. So in your main function, you will define one message LCD as a result. So after that, setting the direction for two of the port D and E. These are considered connected into the LCD interfacing. One for data line, other for control line. Here I haven't mentioned the analog channel for A and 0. So input direction is the status for that pin. But as after the reset, every controller pin will act like a input. So at least for PIC18 controller, this pin is after reset act as an input. So I haven't mentioned. For the LCD initialization, we need to start our conversion. With the help of start of conversion, we will initiate the ADC conversion. Now this is mentioned in while loop. So as we wanted to continuously monitor the in while one, as we continuously wanted to monitor this conversion, so we initiate call the function as a start conversion and get result. Whatever result will be there, that will be stored in ADC valve variable. Now in this variable, as we wanted to display this result in LCD, we need to convert that respected data into ASCII format, because whenever you are giving any kind of data which is to be printed on LCD, we need to convert it into ASCII format. So for that purpose, we'll assume that 4-digit number we wanted to print. That's why we will convert this AD val register divided by 1000. So whatever remainder will be there after this conversion result, that will get stored in I variable. And in ASCII conversion, the ASCII hex number to display 0 to 9, we have ASCII hex value as per the ASCII table 30 to 39 hex. So in that remainder, we'll be adding 30 into it. This will be nothing but your thousands place. That's why we have taken this as a 1000. And this 1000 we have divided with the help of whatever result will be there from ADC. From that we have divided this 1000. After that, similar condition we have to apply it for the 100 place. So in that manner again for the 100 place, so for whatever previous result was there, that was I, again will get divided by 100. So whatever remainder will be there, in that remainder we are simply adding 30 into it, and immediately with the help of LCD data function we are displaying that 100 position. So like this way we need to write the function with the case of all the 100 position, tens position as well as ones position. So in that manner you will able to have the condition for all the places for 1000, 100 and ones place. So like this way, once you complete with that ones position and 100 position, code will get over. So like this way you will able to write ADC program for PIC18 interfacing.